Toyota has named Koji Sato as its new president, with the Lexus president becoming the new CEO and Akio Toyoda stepping into a chairman role. While some criticize Toyota's position in the fully electric vehicle space as others race toward an all-electric future, Toyota has introduced a significant innovation that has captured the automotive industry's attention. Imagine an engine that delivers the sound and performance of a traditional sports car yet emits nothing but water vapor from its tailpipe. This is not a distant dream. Toyota's hydrogen combustion engine is already being tested on racetracks in Japan and is challenging conventional ideas about zero-emission vehicles. This project represents a major commitment from Toyota, asserting that the internal combustion engine is not obsolete but simply requires a new fuel source. The technology is fascinating. Most people are familiar with fuel cell vehicles like the Toyota Mirai, which generate electricity through a chemical reaction between hydrogen and oxygen. However, hydrogen combustion engines operate differently. They burn hydrogen directly using modified fuel supply and injection systems adapted from traditional gasoline engines. In essence, Toyota has refined an existing engine platform with hydrogen technology. The core of this development is a modified 1.6-liter turbocharged 3-cylinder engine from the GR Corolla and GR Yaris. This was not a simple fuel substitution. So, hydrogen burns faster and hotter than gasoline, which means, engineers have to reinforce critical components. This includes using hardened valves to withstand those extreme temperatures, strengthened connecting rods to handle the intense combustion forces, and, of course, specialized fuel injectors that are designed specifically for hydrogen's unique properties. The result is an engine with excellent responsiveness thanks to that faster combustion, while still maintaining driving enjoyment through sound and vibration, except for trace amounts of engine oil that might get burnt during operation, which honestly, is an issue you'll find in gasoline engines too. Hydrogen combustion engines emit zero carbon dioxide. Racing in this case actually serves as Toyota's development laboratory. The company didn't just stop at building the engine, they went further and put it through the demanding environment of endurance racing. Since 2023, Toyota has been competing in Japan's Super Taikyu Endurance Series with a hydrogen-powered GR Corolla, marking the world's first racing vehicle to use liquid hydrogen fuel. This provided invaluable real-time data, accelerating development far beyond standard testing. The outcomes have been remarkable. Over one Super Taikyu season, Toyota increased hydrogen combustion power by 24% and torque output by 33%, achieving performance comparable to conventional petrol engines. Range improved by approximately 30%, and refueling time decreased from about 5 minutes to just 1.5 minutes. This progress demonstrates significant gains in both performance and efficiency within a short time frame. Notably, Toyota Motor Corporation's chairman, Akio Toyoda, participated as a driver under his racing name, Moraizo, personally testing the vehicle. A major advancement has been the shift from gaseous to liquid hydrogen. Early prototypes used compressed gaseous hydrogen, which had limitations. So, liquid hydrogen actually doubles the cruising range while keeping the refueling time at about 1.5 minutes. But, storing and handling liquid hydrogen at temperatures below -253 degrees Celsius brought up some challenges, like developing fuel pump technology that works in those super low temperature environments and figuring out how to prevent hydrogen evaporation. Toyota also managed to achieve quite a bit of weight reduction, shedding over 50 kilograms from the GR Corolla H2 concept in just 2 months of development. The move to liquid hydrogen made it possible to design a more efficient tank. Since liquid hydrogen operates at lower pressure than gaseous hydrogen, Toyota went with an oval-shaped tank that makes better use of the cabin space, giving you, 1.5 times the capacity of the old cylindrical tanks. This actually doubles the hydrogen volume and cruising range compared to the previous compressed gaseous systems. Plus, by using liquid hydrogen, you can do away with the compressors and pre-coolers that gaseous hydrogen stations need, which means fueling stations can be, get this, 4 times smaller. When it comes to performance, Toyota's hydrogen engine actually delivers up to 400 horsepower, which rivals some of the brand's most efficient engines. So, this is not just some modest eco-car performance, it's real, legitimate power. Plus, the faster combustion rate means you get immediate throttle response, offering a level of driving engagement that honestly, electric vehicles often lack. On the track, these vehicles really show off sustained capability. For example, during the Fuji 24-hour race using liquid hydrogen, the car managed to complete the event with only 25 pit stops. That's a big improvement compared to 41 pit stops the previous year, when they used gaseous hydrogen, and they averaged about 14.3 laps per stint. For everyday use, Toyota introduced the Corolla Cross hydrogen concept. Their engineers equipped the 1.6-liter three-cylinder turbo engine from the GR Corolla with high-pressure hydrogen direct injection technology, and that's actually borrowed from motorsport. They also used hydrogen tank packaging expertise from the Mirai, resulting in a prototype that can carry 5 passengers along with their luggage. So, this is a fully functional family vehicle, not just a compromised test model. The high-pressure direct injection system, ensures solid performance, while proven fuel cell tank technology safely stores hydrogen. Real-world evaluation, including winter testing up in northern Japan, is still ongoing. Toyota reports being approximately 40% along the path to commercialization for products like the Corolla Cross H2 concept, though it's not yet certain if the technology will mature enough for road cars. There is, however, clear potential for application in motorsports, engineering, solutions, and patents. The development involved overcoming numerous engineering challenges. Hydrogen combustion engines actually produce more moisture internally than conventional engines. To address this, Toyota patented improved crankcase ventilation systems with more robust PCV valves, specifically designed to handle that extra moisture, which is really critical for engine longevity and reliability. The company also developed water-cooled hydrogen engine technology with strategically placed water injection valves, dual injection timing, and evaporation management. This system manages the higher operating temperatures of hydrogen combustion engines, enabling high-performance applications. Environmental considerations were also integrated. Carbon capture technology was incorporated, using the engine's large volume air intake and generated heat to capture carbon dioxide from the atmosphere through devices in the engine compartment. While hydrogen combustion engines attract attention, Toyota continues to advance fuel cell technology. In February 2025, Toyota announced its third-generation fuel cell system, designed for commercial sector needs. It offers durability matching conventional diesel engines, significant improvements in fuel efficiency, and substantial cost reductions compared to previous versions. Market introduction in Japan, Europe, North America, and China is planned after 2026. The improvements are substantial. Durability has increased up to 2 times that of the prior generation, achieving maintenance-free operation comparable to diesel engines. Fuel efficiency improved by 1.2 times, allowing for a 20% greater cruising range. For commercial applications where downtime is costly, these durability enhancements are crucial. Since launching the Mirai FCEV in 2014, Toyota has sold approximately 28,000 units across more than 30 countries. Since 2019, Toyota has supplied over 2,700 fuel cell systems to more than 100 customers globally for applications including buses, railroads, and stationary power generators. One may question why pursue hydrogen complexity when battery electric vehicles exist. Toyota's answer is that one size does not fit all. The company believes placing all emphasis on electric vehicles is unwise and remains committed to a multi-technology approach, including hybrids, plug-in hybrids, battery electric vehicles, and hydrogen fuel cell vehicles to meet diverse global customer needs. Hydrogen offers some practical advantages. Refueling only takes a few minutes, which is pretty comparable to what you'd expect with gasoline. On the other hand, charging an electric vehicle can take hours, even if you're using fast chargers. This time difference is operationally critical for commercial fleets and long-haul applications. Hydrogen technology doesn't rely on lithium, nickel, or rare earth elements, so it avoids concerns about problematic supply chains and the environmental impact that comes from extracting those materials. Furthermore, hydrogen combustion makes use of existing internal combustion engine manufacturing infrastructure, which means that infrastructure doesn't become obsolete. The primary challenge right now is the current scarcity of hydrogen fueling stations. Without accessible refueling infrastructure, even the best hydrogen vehicle, honestly, has pretty limited utility. However, the market is expanding rapidly. The hydrogen fueling stations market is expected to grow from $500 million in 2024 to $1.8 billion by 2030 with a compound annual growth rate of about 23.8%. This growth is being driven by government incentives and corporate commitments all around the world. One big advantage of liquid hydrogen is that stations can be 4 times smaller than gaseous hydrogen stations, which really helps reduce real estate requirements and construction costs. For example, Toyota's own Port of Long Beach Processing Center built a first-of-its-kind tri-generation system with fuel cell energy, using renewable biogas that's converted to hydrogen, and it produces 2.3 megawatts of electricity.